In this mini lecture, we're going to do a brief introduction to limits. So let's begin with a simple function. Let's say our function is f of x is equal to 2x plus 5. All right, so let's go ahead and graph this linear function. I'll make a rough sketch here. Looks to me that the y-intercept is 5, so I'll go up to 5, make a point, and the slope looks to be 2 over 1. So we'll go up 2 and over 1, make the other dot, connect the dots. All right, so this is the graph of f of x equals 2x plus 5. The y-intercept was 5, and the slope was 2, or 2 over 1. All right, so let's take a look at this a little bit further. Let's say we want to plug in, let's just use the number 3. And we want to plug in 3 for x into the function. All right, so if we plug in 3 to x, that'll be f of 3 is equal to 2 times 3 plus 5. 2 times 3 plus 5, we get 6 plus 5, and we get 11, right? So a solution for our function is 3 comma 11, and it lies on the graph of f of x, right? It lies on that graph. So if I were to go back up to it, I would go to 1, 2, 3, and we said this was going up 5, 6, 7, 8, 9, 10, 11. So it's about right there somewhere, right? So it lies on that line, 3 comma 11, on that line of that function f of x. All right, so we did that. Now let's just change our talk just a little bit, right? Change our talk just a little. Now let's say as we get closer and closer, right? Sorry about that. We get closer and closer. And we want to get closer and closer to x equaling 3. So the height of the graph gets closer to y equals 11, right? So as you get closer and closer to x equals 3, the height gets closer to that y equaling 11 that we just looked at. All right, so think about this. Let's take a look at this. Let's say that x is 2.9. All right, so let's input that into our function, f of 2.9. So that's going to be 2 times the 2.9, and I'm just inserting this into that original function of 2x plus 5. So 2 times 2.9 plus 5, crunch those numbers, we get 10.8. Think about this a little bit further. Let's say our x is 2.95. So f of 2.95, we just substitute in 2.95 times 2 plus 5, crunch those numbers, we're going to get 10.9. All right, I'm going to do this one more time, and then you'll begin to see this a little bit more clearly. 2.99999. So let's take f of 2.99999, and that's going to be 2 times 2.99999 plus the 5, crunch those numbers, and we'll get about, let's see, my calculator is giving me 10.99998. All right, so as we increase that x value, 2.9, 2.95, 2.99999, that y value is 10.8, 10.9, 10.99998, right? So f is headed straight for 3 comma 11. It's going really towards that. So this is what is meant by the limit when we say the limit. So what is the limit? Formally, we can just say it's the intended height of a function at a given value of x, right? That's the intended height of a function at a given value of x. All right, so that can be known as the limit. All right, let's look at the notation that we use for a limit. The notation. So we use lim, and I'm just writing it in cursive, but you can write it in normal print. Lim f of x equals 11, and right under it I'll have an x, maybe a small arrow with the 3. So what does it say? To read this notation, for us it says that the limit as x approaches 3, the limit as x approaches 3, and the limit as x approaches of 3 of f of x equals 11. All right, so the limit as x approaches 3 of f of x equals 11, or sometimes you can change things around a little bit, right? You can just say the limit of f of x as x approaches 3 is equal to 11. So 3 is the number you're approaching. 3 is the number you're approaching. That f of x is the function in question. And that 11, that's the intended height of f at 3. All right, let's take a look at a more involved example. Let's say we have the example of g of x is equal to x squared minus x minus 6, and divide that by x plus 2. So let's go ahead and maybe sub in x equals negative 2. Sub in x equals negative 2. So then we have g of negative 2 equals negative 2 squared minus negative 2 minus 6, all divided by negative 2 plus 2. All right, crunch those numbers. We'll get 4 in the numerator. 2 squared, negative 2 squared is 4. And the negative of a negative 2 makes that a positive 2. So 4 plus 2 is 6, minus 6. And that's 0. In the denominator, we get a 0. So we'll get 0 over 0. All right, so 0 over 0. For us, this is known as indeterminate form. Indeterminate form, when we get 0 over 0 or infinity over infinity and things like that. That's indeterminate form for us. So what does that mean? That indeterminate form means that there is a hole, that a hole appears in the graph at that value of x. So there's a hole in the graph of our function g of x at the value of negative 2 for this specific example. So let's go ahead and take a look at it. Just go ahead and draw a brief rough sketch. So it looks something like this. Let's say we go down 1, 2, 3, 4, 5, I'll say. It's going through 3, I know that much, and I've already figured out the graph to this ahead of time. So to save us some time from doing this, you can also pop this into some technology like a graphing calculator or Desmos or something. All right, here we go. All right, so at this value, at x being negative 2, so the order pair negative 2, and that's what, negative 2 comma negative 5, we see that hole that appears in the graph of our function. So we will still evaluate the limit at x equals negative 2. Right? Still evaluate the limit at x equals negative 2. It doesn't have to exist, and I'm talking about When I say it doesn't have to exist, I'm talking about the function. It doesn't have to exist at a certain point for a limit to exist. The function only has to have a clear height that it intends to reach. All right, so let's go ahead and evaluate. The limit of our function g of x. We already identified g of x a few moments ago as x approaches -2. All right, so if x is -1.99999, we can say g of -1.99999. Crunch that in the calculator, do all the number crunching on your own. If you can push pause, do so. And then do that number crunching and you should get -4.99999. So this shows that the function intends to reach a height of -5, right? It intends. Thus, the limit as x approaches -2 of our function g of x is -5. So even though -2, -5, that ordered pair does not appear on the graph, the limit still exists. All right, so our next topic in our introduction to limits are one-sided limits. So when we look at functions, functions will usually intend, we said, to reach two different heights at a given x. So one height as you come from the left side, and one height as you come from the right side. So a function will intend to reach two different heights at a given x, and one height as you come from the left, one height as you come from the right. So thus we have what are called left hand and right hand limits. Left hand and right hand limits. So let me give us another rough sketch of a graph of a function. And we'll take it up to, let's see, 3, 4, 5, 6, and over 1, 2, 3, 4. So at 4, 6, I'll make an open circle, and graph can look something like this. So we said that's at 4, 6. And then there's another piece to this graph. Let's see, at 4, 2 will be right here. We'll close that circle right there. Maybe it'll come down and go up a little bit. So this is the graph of the function. We'll call it h of x. H of x. So left hand and right hand limits. Usually for us, this is the result of a piecewise defined function. So let's take a close look at it, and let's look at where x is equal to 4. Let's look directly where x is equal to 4. So you can see at 4 we had 4 comma 6 as an open circle, and this was, what was this? We said this was 4 comma 2. That's a closed circle there. So approaching from the left, right? So from the left, the function intends to reach 6. You can say intends to reach 6. So we can write down that we have the limit of h of x as x approaches 4, and it's from the left. So to the right of the number, we're going to use a minus sign to indicate we're coming from the left, and then it equals 6. So the limit of h of x as x approaches 4 from the left is 6, right? We can see that. Now, approaching x equals 4 from the right, it looks to me that it intends to reach 2. It intends to reach 2 from the right. So I'll write that limit for that side as the limit of h of x, and this will say as x approaches 4, and since I'm talking about from the right to the right of the number, I'm going to write a plus sign. So from the left, I'm going to write a minus sign to the right of the number, and to the right of the number, I'm going to write a plus sign from the right, and that's equal to 2. Right? So two different ones. Approaching x equals 4 from the left, the function intends to reach 6. So I write the limit of h of x as x approaches 4 from the left equals 6. And then approaching x equals 4 from the right, the function intends to reach the height of 2. So the limit of h of x as x approaches 4 from the right, denoted by that plus sign, is equal to 2. The next topic in our intro to limits is finding when does a limit exist. So there must be three things that must occur, and these must occur for a limit to exist. So the first thing is the left-hand limit. That left-hand limit that we get must exist at x equals c. It must exist at x equals c. All right. Then also we have to say in a similar way that right-hand limit that we get must exist also at x equals c. So they both must exist at x equals c. All right. And then the third thing that must occur is that the left and the right-hand limit, at c must be equal. Got it? So the left and right-hand limit at c must both be equal. All right, so those are the three things that must occur for a limit to exist. So in a lot of calculus books, in a lot of textbooks, you'll usually see it written as such, right? They'll usually say something like the limit of f of x as x approaches c from the left, right? If the limit of f of x as x approaches c from the left is equal to the limit of f of x as x approaches c from the right, then they'll say then the limit of f of x, that function, as x approaches c, well, it exists and is equal to the one-sided limits. It exists and is equal to the one-sided limits. So let's go ahead and take a look at an example and see what we have here. So let me draw another rough sketch really quickly. So I'll take it up to 5, my y-axis, and I'll take it over to 6 tick marks, 6 on my x-axis. All right, so I'll say I'll be at about 6, 5 for this point here, and maybe it extends up and then goes, looks something like this. I'll call this point right here -1, 5. -1, 5. And I said this was 6, 5. Let's clean that up a little bit. All right, -1, 5. Yeah, that's much better. And then I'll put another piece to the function over here at 6, 1, and we'll have a little hole right there. It's 6, 1, and maybe it'll go down and up a little and then back down, something like that. All right, so look at the values at where we have x is equal to -1 and at x is equal to 6. X is equal to -1 right over here and x is equal to 6. Let's take a look at those values. All right, so as we look at those, the limit of our function as x approaches -1, you look at that, and we can say that the limit of f of x as x approaches -1 from the left is 5. And I'm gonna write underneath it, the limit of f of x as x approaches -1 from the right is equal to 5. And you see that they're equal, right? They're both equal to 5. And then the general limit, the limit x approaches -1, we can say f of x equals 5. So for us, the limit exists. That limit exists. All right. We can even go and look at our next one would be maybe the limit of f of x as x approaches 6. All right, well, let's take a look. So we look at the limit of f of x as x approaches 6. Let's look at it from the left. From the left, if you go back and look at the graph, you may have to rewind a little bit if you didn't copy it down. We see that equals 5. And the limit of f of x as x approaches 6 from the right, you see that going from the right hand side, it approaches 1. So you look at those two, right? They are not equal. So the limit does not exist. It does not exist. All right, so the final quick topic in our introduction to limits is, when does a limit not exist? All right, so I have this function already drawn out for us, and at that value c, we have a closed circle. It's going to the left, and at this value c as well, up above, we have an open circle, and it's going to the right. So here is where you can see, you can plainly see that the right and left-handed limits, right? The right and left-handed limits, and you guessed it, they are not equal. So here's where a limit does not exist, when the right and left-handed limits are not equal. Okay, let's take a look at another situation. So maybe my function looks something like this, and you see that dotted line. You know what that is, right? That's a asymptote, and for us specifically, it's a vertical asymptote, and we'll call this value c. So we'll say at x equals c, we have a vertical asymptote. So here our function increases. You see it increases, and it's going up and up and up, but never touching each other, never crossing that asymptote. It increases without bound. So this is another situation where a limit does not exist for our function. All right, so another situation, and here, this might be rough for me to sketch. It's just going a little crazy right there. So it's oscillating infinitely. It's oscillating infinitely. So this is a rare case. So maybe if we have y equals sine of 1 over x, right? And then we're to find the limit of sine of 1 over x as x approaches 0, let's say. So the function never settles on any one value the closer you get to x equals 0. It's just oscillating infinitely. It never approaches a single height in this case. So Thus, here we have when a limit does not exist.